Welcome back. So, last time we were speaking about this bioamplifier and its implementation on the breadboard. Did you try to mount it? Did you find any difficulties?
No. Yes. Yes, I think we all have
So you were able to mount it?
Yes.
Okay. So there were a couple of things I didn't tell you, so I wanted to see whether you could realize about this or not, but now I reveal the tricks. So if you see this schematic and if you try to mount it on the breadboard, you will see, of course, there are a couple of things that are different respect to the pictures. So if you follow the pictures in order to reproduce this circuit, the pictures that were included in the GitHub repository, you will notice that there are a couple of differences. So the first difference, of course, is that these external noise components are not present, because this is a sort of add-on, something that I added in order to represent the noise. So this R noise 1 and R noise 2 resistors, and of course this V external noise generator, these are not present as components on the breadboard. And similarly, the neuron and the two resistors for the electrodes are not present, because this is just a circuit that will simulate an input, which will be, in our case, our bicep muscle. So these things are not there in the circuit. Then there are another thing which is not present in the circuit, which is this random noise voltage generator, which is used in order to simulate the noise coming from the power supply. And of course also the power supply is not present as a box, but it's basically the two pins G and D and plus 5 volts on the Arduino. And then there are another couple of components which are not present in the circuit, which are those two resistors, RC1 and RC2, having a very high value of 10 mega ohms. So before we verify what you mounted on the breadboard and we proceed with the simulation and also with the experiments, I want to say a couple of words about those two resistors and the reason for which this schematic diagram is a little bit different than the one you have. So the first reason is that when you want to simulate something, you need to attach the sources. So you cannot simulate the behavior of a circuit if you don't stimulate that circuit. And to stimulate, we have to power it up. So that means connecting to a power source like this one. So we have to introduce a fictitious symbol, a fictitious power supply in our schematic diagram. And also, of course, the stimulus, so the signal and the noise at the input. And then there are another couple of things about those two resistors. So let's try to understand what this circuit is doing. So we said that at this point, let's say differential input black box, we have two signals. One which is called signal and the other which is called reference. These are voltages respect to a ground point in our circuit, and we said that our ground point in our circuit is this connection here, this node, which comes from the virtual ground circuit that we already discussed. So our neuron and the reference voltage are referred to that ground point. So those two signals goes into these two amplifiers, so U1D and U1A in the schematic diagram at the plus input, and this box here is the feedback network. Feedback network that has its inputs here on the right in. Then the signals are fed back through those resistors R1, R2. Then there are those two capacitors, and the output of this feedback network goes to the minus of the two operational amplifiers. So let me switch for a moment to the blackboard. Okay. So if we simplify our circuit, just concentrating our attention on the amplification stage, let's say where the magic happens, this is the circuit we have. This feedback network is here labeled with the Greek letter beta. So we have a differential input amplifier, a differential output, and then later on at VO and VO prime we will attach a difference amplifier that just computes the difference between the two signals, but the amplification occurs here. So how does it work? We did something similar during the theoretical part of the course. So we said that an operational amplifier is a device having a so-called open loop gain A, which is this, which can be very high, like 10 to the 8, something like this, with the idea to approximate this to infinity. Then the amplifier will take the voltage at the plus and minus input, so I'm speaking of this voltage here and this voltage here at those 2 points. So V plus minus V minus, the difference, because every operational amplifier is itself a differential amplifier, and it multiplies by coefficient A, and that's VO. And similarly for the other one, so VO prime is A multiplied V plus prime minus V minus prime, the voltages at its inputs. Okay, so we can simplify this relation a little bit. So if I take delta VO, so I'm now interested in the difference of voltage between VO and VO prime, and I call it delta VO. So by just making a difference of these two equations, which is the, let's say, simplified model of the operational amplifier, then I get this. Delta VO equals A multiplied delta V plus minus delta V minus, where I define the delta V minus, delta V plus is equal to delta VI, and delta VI is here, the difference between VI and VI minus, so differential input, and delta V minus is the difference between the voltage at the 2 minus of the operational amplifier, what here is represented in green. So it's this voltage between this point and this point, which is the output of our feedback network. The input of the feedback network is delta VO. So now we want to understand what this circuit is doing, and therefore we need to write the equations. So this is the equation we are interested in. It is telling me that delta V minus, the output of this beta block, is beta, which would be the transfer function of this block. Remember, the transfer function of a two-port network is what connects the input to the output of the two-port network, and beta is a two-port network, so the input port and the output port. So the output is the transfer function multiplied the input. Okay, so let's try to understand what it does. So we have to make a couple of substitutions in order to understand this. Okay, so let me see. Delta VO equals A multiplied delta V plus, but we called it delta V input, A multiplied this minus A multiplied delta V minus, which we called beta delta V output, like this. Okay, so we do this, delta V output plus A beta, sorry, there was a delta here, A beta delta V output, so this is delta V output plus A beta delta V output, equals A delta V input, which means that delta V output multiplied 1 plus A beta equals A delta V input, and then I want to calculate this quantity, delta V output over delta V input, which is A divided 1 plus A beta. And what I'm interested in is to calculate the gain of the amplifier, which is the limit for A that goes to plus infinity in this approximation of the ideal operational amplifier of this ratio delta V output over delta V input. And this limit is on the of the case infinitive over infinitive, so we solve it with the L'Hopital rule. That means taking the derivative of the numerator respect to A and the derivative divided by the derivative of the denominator, and this things makes 1 over beta, and I put it like this, 1 over beta of omega, where omega is the frequency. So that means that the output here is 1 over beta multiplied the input. So this is what the circuit is doing. So if we know what beta is doing, then we have to compute 1 over beta, and we know what the entire amplification is doing. So let's go back to the circuit diagram here. Okay. So our circuit diagram is done like this: a resistor, a capacitor, another capacitor, a resistor, and those two resistors. For the moment, let's forget about those two resistors. Let's consider only the two resistors R1 and R2 and the two capacitors C1 and C2. So I go here. And let's draw this circuit this way, let's say in the conventional way. With the input on the left and the output on the right. It's the same of our feedback network. I've just flipped it in this schematic diagram. So we notice that this circuit is similar to a low pass filter. So the low pass filter was something like this. Okay, so let's try to analyze this feedback network that will tell us the behavior of the entire amplifier. So first we can do some simplification in this circuit. We notice that we have two capacitors and they are in series. So in the theoretical part of the course we haven't computed any formula for understanding how to simplify the series or parallel of capacitors. We did this for the resistors. So maybe later on we can do this carefully, but let me just tell you something. So if you remember, when we had a series of resistors, we said that this is equal to a resistor like this, the summation of the two resistors. So let's consider the physical object implementing a capacitor. So a plate like this, another plate like this, and this is our capacitor. If we remember, we said that the capacitance was proportional to the area of the plates. So if now I put another capacitor like this, and I connect it in parallel, so basically what I'm doing is I am building a sort of bigger capacitor with the double of the area. So we expect that this is 2 times the capacitance if the capacitance of those two are C and C. So here we have an indication of the fact that what is the series of a resistor in terms of its equivalent resistance is something like what is the parallel of the capacitors. So if we carefully do the calculations, we will find that now I have to delete something, so I delete all of this. We will find that the capacitor behaves differently respect to the resistor in a sort of complementary way. So C1 in series with C2, something like this. Is something like this, the equivalent capacitors. So C equivalent equals 1 over C1 plus 1 over C2, while the parallel of two capacitors gives an equivalent capacitors equals to C1 plus C2. So this means that in principle we can replace this thing with a certain capacitor having this value. So let's do it. I call it C prime. We don't calculate it. R, like this. This is the input of the feedback network, and this is the output of the feedback network. So now I make more room. So we discovered that our feedback network is something like this. Okay, so now let's try to compute the transfer function beta of omega, which would be V out over VE. So this circuit is like this, and there is a current I flowing here. So remember that this circuit is now stimulated by an input voltage that is a generic voltage, so it can be an alternate sinusoidal signal, it can be a pulse, it can be noise, it can be whatever. And if we remember what we did during the course, we studied the impedance concept, and we said that for a capacitor there is a sort of resistance that depends on the frequency, and we call this this resistance dependent on the frequency, we call it impedance. And the capacitive impedance is 1 over SC for a capacitor, where we put S equal I omega, and omega is the frequency. And we said that we can replace the impedance for the capacitors and think that everything is made of impedances, and the impedance of the resistor was just equal to the resistance. So now we can calculate the current I as the voltage V input divided the summation of those three impedances which are in series. So the circuit is now like this. Okay, so this is ZR, and ZC, input and output. So those three impedances are in series, and therefore the current I is V input divided the equivalent impedance of a series of impedances, which is just the summation. So it's ZR plus ZC plus ZR, which is V input divided to ZR plus ZC. And now that we know the current is flowing in series, so it's flowing in ZR, in ZC, and in ZR, and so specifically is flowing in ZC. And so again, with the Ohm's law, which is what we applied here, we can calculate the voltage V output across the impedance ZC. So V output is the impedance ZC multiplied the current I. So it is V input ZC multiplied to ZR plus ZC. I just substituted this expression for the current I. And now we can replace the value of the impedances with what we know they are. So it's like this. And let's do a step forward also. Let's calculate the ratio VO over VI, which is what we call beta of omega. That is V output of omega divided V input of omega. and this thing is ZC over 2ZR plus ZC, which is 1 over SC divided 2R plus 1 over SC. And if I multiply the numerator and the denominator by SC, then I get 1 over 2 SRC plus 1. Okay. And this thing is exactly the normal form of a low pass filter that we studied during the course. So we verified that this beta of omega, this is beta of omega, if you put omega, I omega in place of S, beta of omega is a low pass filter, and so the resulting amplifier has a transfer function which is 1 over beta of omega, so it's something like 1 over a low pass filter. So if we remember the transfer function of a low pass filter, omega, and let's call it beta of omega, so it was something like this. It was flat till a certain point we called omega c, the cutoff frequency. So 1 over beta of omega, now it's a little bit let's say more difficult to visualize, but let's say it's 1 over this value, which is I don't know what, maybe this, and for high frequency this thing becomes very small, and 1 over something very small is a number that becomes very big. So I don't know the exact shape, we need to calculate it carefully, but it's something like that. We expect that after a certain frequency it will amplify the signals a lot, and before that frequency, notice this gap difference in the amplitude, it will not amplify, it will suppress. So it's a sort of high pass filter, but not exactly the high pass filter of the first order we are used to know, because that would be 1 minus beta, not 1 over beta. So I can tell you that if you do this, this resulting low pass filter would be much steeper than the first order filter. So it's called a reciprocal filter because it's computing this, but it's a sort of high pass filter, and that would be good for our neurons, because we know that the neural pulses are something like this, let's say. So we want to keep those high frequency features, and we want now to suppress slow variating signals, like let's say like this, maybe. I mean, all these slow trends we want to suppress, also because it might contain noise coming from the 50 Hz power supply from the mains, 220 volts at 50 Hz. Okay, so now we understood that the resulting amplifier is a sort of high pass filter.